Okay, so now we're going to try to apply bonding, molecular orbital bonding to a polyatomic um, molecule. In this case, we're going to look at a very simple one. We're going to look at the trihydrogen cation, so H3 plus. So this is going to be a cation that is made up of 3 hydrogen atoms, 3 hydrogen nuclei, and only 2 electrons because it's a cation. So it'll be a relatively simple thing to look at. Okay, so let's look at this in a couple of ways. We're going to start by looking at this with a linear arrangement of molecules, of atoms in the molecule. So that is, we're going to take each hydrogen atom, which has a 1s orbital, and we're going to make a straight line molecule out of it. So that's going to give it a linear geometry. So we're going to construct the first molecular orbital of the constructive overlap between all 3 of the orbitals. So if we take each of these hydrogen 1s orbitals, 1sa, 1sb, 1sc, just for convenience, put them A, B, and C. And we're going to add all 3 of these together in one overlapping bonding orbital. The way we're going to sum up those contributions, we'll get a sigma orbital in this case because it will have cylindrical symmetry along the bond axis. We'll see that in just a second. This is going to be the first orbital, so we'll call it 1 sigma, and it's going to have that even symmetry with respect to its center of inversion. Center of inversion of this, in this case, is going to be right at the central point of the hydrogen B, so the central hydrogen. Okay, so what does that overlap look like? It's going to just look like that. With that blue line there shown on the screen, that's showing you the bond axis between the nuclei. So essentially, that blue line is a straight line being drawn from the center of atom A to the center of atom C. And it's going to go right through the center of atom B on the way, because this is a linear geometry. So this overlap, as it's a completely bonding orbital, it has no nodes. It's going to be the most stable because it has no nodes. And most stable basically just means that it's the lowest in energy. So that's our first orbital, that's our bonding orbital, and we will put that down there. So that is our 1 sigma G orbital. Okay, so now let's look at the next orbital. For the second orbital, we want to look at, it's going to have to include some destructive overlap because we can't just add all 3 of them together. The next linear combination of atomic orbitals is going to involve some kind of addition and subtraction of these orbitals. So in this case, it turns out that it is going to be the addition and subtraction of the hydrogen 1s on the A hydrogen and minus the 1s on the C. So that is going to be destructive interference between those 2 orbitals. The central hydrogen's 1s orbital is at the wrong geometry to contribute to this wave function. Because if we left it as a plus sign, then it would constructively overlap on the left side with the A, but destructively interfere with the negative sign on the C. So it would have a net non-bonding effect. And if we flipped its sign to minus, it would do the same thing. It would destructively interfere with the A and constructively interfere with the C. So again, a net non-effect. So really, it just doesn't participate, or that's the way mathematically that we're going to analyze this. So there's no contribution for this orbital to the central of this orbital to the molecular orbital. So we're going to add up our coefficients, and we're going to get a sigma orbital. This time, the sigma orbital is going to have the asymmetric asymmetric symmetry. Every point on the left will be inverted through the center of inversion, and we'll have a negative sign of the wave function on the other side. And the coefficients of the wave functions are just going to be the square root of 2. That's how we add up two separate wave functions to keep our overall wave function normalized. I didn't mention, but in the last slide, when we had an equal contribution, well, we had an unequal contribution from our orbitals. So the end atoms had the square root of 0.25, and the central atom was the square root of 0.5. So we'll have a similar mathematics in the last orbital and a different geometry. So I'll point that out in the next slide. Okay, so what does this one look like? When we do that, it looks a lot like our sigma antibonding orbital that we saw for H2. And actually, that's an important point. I'm going to come back to that in a couple of slides, and we're going to analyze this in a second fashion after we go through this, this process first. So it shouldn't really be that surprising that that looks like a hydrogen 1s, or sorry, a hydrogen 2 sigma antibonding orbital, because we're only taking the negative overlap, the destructive interference between the hydrogen on the right and the hydrogen on the left of their 1s orbitals to create this molecular orbital. Well, that's exactly what we do in the case of H2 molecule. So we get the same thing. The only difference really here is that the bond length is much longer because we have to leave a space in between for the other hydrogen. So this is a really long bond length for H2. That's what this orbital looks like. Okay, so this orbital has one node, like our regular antibonding orbitals. It has the middle stability of the three orbitals that we're going to make here, and the middle energy, which those are synonymous terms. So we'll just grab that and we'll put that over there, and we'll clean off the board, and we'll look at our last orbital that we're going to make. These three atomic orbitals are going to make three molecular orbitals. So the third molecular orbital is going to be made up of the destructive overlap of all three orbitals. So how are we going to do that? Well, we're going to, in this case, subtract the one on the left, the A, add the one in the middle, and subtract the one on the right. The signs are arbitrary. We could have plus, minus, plus. Here we're just doing minus, plus, minus. It works out to be exactly the same thing. It's just whether the wave function is got a positive sign or a negative sign. Remember, the wave function having a positive or a negative value doesn't affect the probability of finding the electron, doesn't affect the energy of the electron. So all of that is just a mathematical designation. But the idea here is that the combination here is going to be our sigma antibonding orbital. It returns to the even symmetry with respect to inversion. So we get that G, we get an antibonding orbital this time, so we'll put a star on it. Now I didn't put a star on the other one, and I'll explain why that is in a second. This one is definitely antibonding. It has as much interference between the orbitals as we can get. And if you look at those coefficients in this form of the wave equation, it is minus the square root of a quarter times the wave function on the A atom's wave function, plus the square root of a half on the central atom, and then minus the square root of a quarter on the end atom. That's just the way these contributions are going. They're not equal contributions because they're not in an equal arrangement. So that is how these wave functions overlap. And it leads to this orbital, which looks a little bit like the bonding orbital between two PZ orbitals, right? Where you get the central part as constructive overlap. But in this case, it's not. This is all destructive interference between each of those orbitals. And that's our third orbital. We're taking three atomic orbitals and we're going to make three molecular orbitals, and that is what our molecular orbital looks like. It's got two nodes It has the worst stability because of these three, and it is the highest in energy. So we will move that over there. And those are our three orbitals made up of those three atomic orbitals, those three different arrangements. Okay, so we're going to continue with this analysis of the linear arrangement of this molecule. But I want to think about this in another way. We're going to picture the same situation, but instead of thinking about how all three orbitals are going to overlap with each other in those three different ways, I want to think about it sort of part by part, and maybe we'll get a better understanding of what's happening. Okay, so let's start with the hydrogen atoms on each end, the A and the C position, right? And like I said before, we can think about these two hydrogen atoms. Let's ignore that central one, the B atom, and just think about how these two hydrogens would form an H2 molecule if it ignored the central atom. So we'll start, they each have their 1s orbitals, the one on the A atom and the one on the C atom. And we're going to look at how these play against energy. So we're building our atomic orbitals. Our energy scaffold. So this is where they fall. We're going to put them right in the middle because we know if we have bonding, the energy will go down. If we have anti-bonding, the energy will go up. So I'm going to start right in the middle. This is the energy level of an individual hydrogen atom not bound to anything. So just H, right? One proton, one electron out in nature all by itself. This is where its energy level is. Okay, so what's going to happen if we consider just the way these two orbitals interact with each other? Well, we're going to see, we know what happens, right? Two s orbitals are going to have bonding and anti-bonding. That's what they do. The only difference between the bonding and anti-bonding between these two hydrogens and the one we saw in the last lecture is that these are really far apart. So we're going to call this a symmetry adapted linear accommodation, SALC, and we'll calculate then, or we'll schematically show what happens with the bonding and the anti-bonding here. So here is the H2 SALC, and we'll look at what happens. We get bonding and anti-bonding. Now, I'm not drawing this as a very big splitting. Normally, we would expect a bigger splitting, on the page because we have all this room to work with. But this is really small, relatively speaking. Why am I leaving so much extra white space? Well, because I know what's coming next. But the reason is because the splitting here is relatively small because the two atoms are so far apart, right? They are distanced by a whole nother hydrogen atom that's in the middle. So right now it's invisible because we haven't considered its interactions yet. We're only considering the interactions of the two orbitals on either side of the central atom. So the interactions of those with each other is relatively minor. So what are we going to do next? Next, we're going to add in that central hydrogen atom, and we're going to put that on this side. So we're going to have the central atom interact with the two outer atoms as described by that SALC. Okay, the central atom is there in energy, and it's a little confusing. It looks like it's lower or higher. It's hard to see because there's so much white space, but I've drawn that at exactly the same energy as the other two individual hydrogen atoms, right? So that hydrogen atom is at just the same energy as the other two hydrogen atoms. And now that hydrogen atom is going to interact with the SALC. So remember, though, it really is only going to interact with the sigma sub g, that bonding orbital, the lower one, because the upper one, if we drop the central atom right in between those, it's going to have a non-bonding interaction with the sigma sub u, the anti-bonding orbital, because if we drop it in as a blue atom, it's going to or a blue wave function, it's going to positively overlap with the A and negatively overlap with the C and have a net zero interaction. If we drop it in as a red orbital, a negative sign, it's going to positively interact with the C orbital and negatively interact with the A and have a net non-bonding. So it doesn't interact with that upper level. It only interacts with the bottom one, the one where both the 1SA and 1SC are blue. And when we do that, it's going to have a bonding, and we will do that now to build the molecular orbitals for H3. And this is just a different way to get the same linear arrangement of those molecular orbitals. But now we're going to see where those energies lie on this energy level diagram. The constructive interference between the sigma sub g and the 1sb is going to take us down to the bottom. And that is the constructive interference where they're all blue. And it's the 1 sigma g orbital that we saw on the last slide. That is the lowest energy level. And at the same time that molecular orbital of the bonding between the 1sb and the Salk of the H2 takes place, we get the antibonding taking place, which goes up from that sigma g up to the top, and that gives us our antibonding. That's why I put the star on this, the 2 sigma sub g for that orbital. So that is the antibonding orbital. Could call that the 3 sigma star sub g. It is the second even symmetry. It's the 3rd sigma. We'll see in it in a second. Anyway, so that is the bonding antibonding. That's only 2 orbitals. We need 1 more orbital. Well, remember I said that orbital just doesn't interact, right? So that orbital is non-bonding. That Salk, the upper Salk, this sigma u from the H2 Salk, is non-bonding with the 1sb orbital, so it just stays at the same energy, and that is our 1 sigma u. So in this type of nomenclature, the way this has been labeled is for every type of orbital, so sigma, pi, you increment the number, the 1, 2, 3. So we start at the bottom of 1 sigma g. Why isn't it 2 sigma u in this case? Well, because it's saying, oh, this sigma u, it's the first sigma u, right? We've had a sigma g, but that's different than a sigma u. So then the next one we go up to, the 2 sigma star g, well, it's a sigma g, happens to be antibonding, but we don't care. Because it's the second sigma orbital with the g symmetry, it's going to get the number 2 as its designation. So those prefix numbers, those change in every different type of analysis. You really have to be careful with how those are written. There's not a systematic, well, there's a bunch of different systematic ways to do it is the problem. Okay, so that is how we apply our Salk and get the this schematic of the energy levels of all 3 of these. And in the schematic, we can see that that 1 sigma u is slightly higher in energy than the regular hydrogen atoms are. So, right, so this is the approach we must use for all polyatomic molecules. And since this is H3 plus, it's got 2 electrons, so I just put in 1 electron, and then the second electron goes in there. So you can see that with the 2 electrons that would have otherwise been in our hydrogen atoms, by putting them into these lower orbitals, we're getting a really good bonding characteristic in this linear arrangement of H3 plus. Okay, so that's one way to think about H3 plus. But then again, there's no reason that H3 plus has to be linear. So if linear is one extreme, then the next extreme is building an equilateral triangle. So we're going to consider that case now as the next possibility for a geometric arrangement, straight line or equilateral triangle. Okay, so let's picture what happens if we take these three hydrogen 1s orbitals arranged in an equilateral triangle configuration and see what kind of orbitals we get when we put them into a molecular orbital structure. Okay, so first we're going to label each of these. It's not as simple as labeling the other ones where we just went A, B, C right across the page. So here we're going to have hydrogen A will be the one that is sort of to the front and the left of the picture. Hydrogen B will be to the right in the middle there. And then hydrogen C is going to be that one at the top and toward the back. So these are the three hydrogen 1s orbitals that in this orientation. And now we want to see how this orientation will build molecular orbitals. We're going to get three molecular orbitals, and we'll have to see what kind of bonding and anti-bonding we get here. So in this geometry, all the atoms are related by symmetry, and so we're going to treat them as a set. Now from group theory, which is covered in chapter 11 of our physical chemistry textbook, which we're not covering this semester, it's something that you'll take in inorganic chemistry instead. The symmetry of this arrangement is known as the D3H. It has to do with the plane of symmetry and the fact that you can rotate it 3 times. If you rotate it by 120 degrees, you get the same orientation, and if you flip it over, you get the same orientation. So this symmetry arrangement has a very specific name, and in group theory, the different symmetry groups have been analyzed. The other thing that group theory tells us is that if we have this symmetry, this D3 symmetry, we're going to get 3 orbitals, and 2 of them are going to be degenerate. Remember, degenerate means that they have the same energy level. So let's see how that comes together. So here are our 3 orbitals. In the first analysis, we're going to do the same. We're going to go about it the same way we did for the linear arrangement. In the linear arrangement, we said, why don't we take the constructive overlap between all 3 of these? And we saw with the linear arrangement, we had the square root of a quarter plus the square root of a half for the central atom plus the square root of a quarter for the end atom. That was the recipe for how to put together the wave functions to build the molecular wave function. In this case, the recipe for the wave function, since they're all equivalent, and we want to keep this as a normalized wave function, the way we're going to do that is add the square root of a third. So the square root of a third is what keeps this as a normalized wave function, because we're adding 3 things, so we add them as the square root of each. That way, when we normalize the molecular wave function, we will get a contribution of 1/3 from each, because it's psi squared d tau. Anyhow, so that's where the values of those coefficients come from. Next is the orbital name here. This orbital name, I don't want you to worry about it for this semester. This comes out of group theory. This is telling us about the symmetry group of this particular orbital. It's what's called an A1 prime symmetry group. So we're going to call this orbital A1 prime. It is a bonding orbital. And when we put it together, it's going to look a little bit like that. So that is a calculated computer-generated surface plot of a 3-dimensional object. But it's the wave function of all 3 of those things combined, sitting right on top of each other. So again, it says no nodes. It is the most stable arrangement, just like in the linear arrangement, and it's going to be the lowest in energy. So that is our A1 prime orbital. We'll put that down there, and we'll erase the board. So now we're going to look at the next orbital. It's going to need some destructive interference, right? Because we can't just have constructive interference. We only get one complete constructive interference molecular orbital. Now we're going to have to start taking linear combinations that include negatives of these wave functions. So the symmetry of this wave function is what's called an E prime. And this is going to be built primarily from, well, not primarily. It's going to have a positive contribution from the 1s orbital on the A hydrogen. So that is the one that is to the bottom left of the screen. And then a negative contribution from the other two. The negative contribution is going to be a lot smaller, but it's going to be from both of them. So that's going to create a shape that looks like this, where we get the positive lobe in the white and in the darker gray in the back, or on the left side. That is the negative amplitude of the wave function from the B and C atoms, because their wave function contribution is negative. So this has one node. It is less stable than the A1 prime orbital because it has that node and it has destructive interference. So it's going to be higher in energy than that A1 prime orbital. So let's just put that up there. And we will move on now to the next orbital, which is also going to include destructive overlap. But in this symmetry, remember, we know that we're going to have two orbitals that have the same energy. They're degenerate in energy. You can also look at this. It is different from the linear case because there's no way to put three things together where you add and subtract and add and subtract where we're going to get two nodes, right? Two of them are going to be positive and one of them is going to be negative, right? Because you can only have one sign on one wave function. We could have a zero, right, like we did in the linear case, but that's still not going to give us a second node. We need to go from positive to minus to positive, and we can't do that with three things in this geometry. So in this geometry, what we're going to get instead of two nodes, we're going to get another wave equation with just one node. Now in this case, the A orbital drops out, it becomes non-bonding, and we only get a contribution here from the B and the C, and those will have opposite signs. And so we get a node that is perpendicular now to the original node from the first one. So this is the same as the other E prime. One node, it will have the same stability as that E prime and the same energy as that E prime. So let's put that up next to that, because those two orbitals are degenerate. They have the same energy as each other. Okay. So what comes next? The doubly degenerate pair of molecular orbitals have that E prime symmetry. Look, although they do not look alike, they have the same energy. That's what doubly degenerate means. So they are constructed in such a way that they'll work out to have exactly the same energy as each other. They have a kind of PX-PY behavior where they're perpendicular to each other. They're orthogonal to each other because they're molecular orbitals. But they're inside this triangular ring of H3. Like I said, each of these orbitals has one node, and they are higher in energy than that A 1' orbital. Okay, so let's put this together and look at the energy level diagram for the triangular cation, the molecular energy diagram. So there's our energy. This time we don't need a Salk. We can't really use it. It's not going to help us. So we're just going to take all three atoms by themselves, A, B, and C, drop those right in the middle of the diagram. So those are just our three individual 1s orbitals of the unbonded free hydrogen atoms before they come together. And then we will build the molecular orbital of the overlap between those three. And what we get is, the bonding orbital is all the way down there with the 1a' orbital, which we saw before, and that is the constructive overlap between all three. And the anti-bonding orbitals, two of them, higher in energy than the unbonded hydrogen atoms, are up there. And those have destructive interference that make them less stable than the individual atomic orbitals from the unbonded case. And so we're going to designate those as anti-bonding orbitals and give them the star treatment. So that's 1e' star. And notice that's 1e'. It's not 1 and 2 because they're degenerate. They're at the same level. They're just referred to as the e' orbitals. Just like we talk about the pi orbitals. Even if there's two of them at the same energy level, it's still the 1 pi orbitals and then the 2 pi star anti-bonding orbitals, which we saw from our diatomic molecules. Okay, so that's that. And again, we have a total of 2 electrons in H3+, so we can put those in, and that's what the orbital configuration for this geometry of H3+ would look like. Okay, so I hope this shows you that molecular orbital theory is providing us a much better model than just that valence bond theory of overlapping or not overlapping, because we can see that even when there's overlapping, there's also anti-overlapping, which creates orbitals that are available even if they're not full. So we'll be able to see in spectroscopy transitions from different orbitals of different symmetries. So the energy difference between that is accessible or investigatable by spectroscopy, for instance. Whereas if we just talked about bonding in a valence bond theory, we would perhaps be able to show that all three of those orbitals just overlap and make a triangle like that, but we wouldn't be able to give a relationship to anti-bonding orbitals that are unfilled, because when we do valence bond theory, we don't think about the anti-bonding. Anyhow, it's a very powerful tool to examine. All right, that is our treatment of hydrogen 3, triatomic hydrogen ion.